Yep.
Yeah, okay. Welcome everyone. I'm very happy to introduce Nick Gurski talking about presentations for action operads. Take it away.
Thank you very much. Thanks for the invitation and for everybody um, showing up. This is based on some joint work with Alex Corner that we actually started a really long time ago. But it came together more completely recently. And I guess even more important than that is I have come to appreciate the stuff I'm going to talk about today about presentations a little more over the past kind of half a year. So this talk is at some level about the question of like what sort of structure do the symmetric groups have? And you can answer this question in a lot of ways, but I want to try to answer it from the perspective of operad theory. In particular, why do we have symmetric operads for the symmetric groups, but we don't have like dihedral operads or alternating operads or something like that? So I'm going to try to explain the kind of structure that you need in order to put this adjective symmetric, as opposed to, like I said, dihedral or alternating or some other family of groups in front of the word operad. And then I want to talk about how we might have a theory of presentations for these things in a very kind of elementary algebraic fashion. So here's the plan for the talk. I'm going to talk about symmetric operads for a little while, and that'll segue into discussing action operads more generally. I'll mention sort of probably the place where this is most likely to appear, these action operads, which is in like, how do you define different kinds of operads? But then, like I said, I really want to focus on this question of presentations. So for that, I'm going to end the talk in kind of two pieces, where we first talk about presentations of action operads from a kind of very general perspective using some locally finitely presentable categories. And then I want to talk about how the presentations that we get out of that theory correspond to presentations of clubs in the sense of Kelly. So let's start by just recalling the notion of a symmetric operad. Now, this is always going to be in the category of sets. So a symmetric operad P in sets consists of a set P of n for every natural number, a specified element that I'll write id in P of 1, although I might accidentally also write 1, but I'm going to try to keep my identity elements and my degree 1 sort of ones distinct. This is a symmetric operad, so it has group actions by the symmetric groups. I'll use sigma n to mean the nth symmetric group, and this is a right action of sigma n on P of n, so we have these for all m. And then we have maps that I'll denote mu. If I'm being really careful, I'll include a whole bunch of subscript natural numbers, but usually I'll just write mu. And this is a thing that I'm going to variously call either operatic composition or operatic multiplication, something like that. And what operatic composition or multiplication does is it takes a single element in P of n, and then it takes n more elements from your operad that can be in whatever degrees you like, in this case, k1, k2 up to kn, and then produces a new element in your operad of degree k1 plus k2 plus dot, 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 up to km. And there are three kinds of axioms that all of this structure needs to satisfy. We need associativity and unit axioms, and then we also need some equivariant axioms. So I'm going to just draw some pictures because I think the pictures are easier than the equations. Okay, so if we've got an element f in P of n, you think of it as an n-ary operation, which is to say a function from x to the n to x. We don't have an x, there is no x here, but if there were, then that's the kind of function that we would think of an element of P of n as. And I'm going to draw this as a little triangle. So this is f, and it's got one output, and it's got n inputs. So this would be like an f in P of 4. It's got 4 inputs and 1 output. Okay. The group actions, we draw those as if they are pre-composition. So if I take the 3-cycle 1, 2, 3, and I take an F that's in P of 3, then my F, recall that I'm going to draw it a little bit bigger. This is my F, and then my permutation. So I'm going to start from the top and go down. So 1 goes to 2, 2 goes to 3, and 3 goes to 1. So this is my new element. So I'm allowed to kind of mix together the elements of my operad and the group elements. Okay. Operatic multiplication, we just draw by kind of sticking triangles together by attaching outputs to inputs. So if I've got, I'll put a G here and it's in, say, P of 3. And then I could put, this will be an F1, an F2, and an F3, and maybe F1 is in P of 2. F2 could be in P of 0, so I won't draw any inputs for F2, and then F3 will also be in P of 3, and so now I've got the operatic multiplication. Mu G is the sort of final one, and then I've got F1, F2, F3, oops, and that thing is now, I just count up how many inputs I've got over here. So this is in P of 5 now. Okay. So these are the kind of algebraic operations we have on our operad. And we've got some axioms. I'm not going to draw the unit and the associativity axioms because that's not really what the talk here is about. Instead, I just want to draw the equivariance axioms. I think it is easier to draw 2 different equivariance axioms, although you can combine these into just kind of like one giant equivariance axiom if you like. So there's one axiom that relates the operatic multiplication of G and then a bunch of F's that have been acted upon with the operatic multiplication of G, the F's with no action, and then a single group element. So let me just draw you a picture, and then we'll see what this says. So if I've got G here, and let's say it's just got 2 inputs, and I've got an F1 and an F2, and then maybe there's a transposition there and a 3-cycle there. So here I've like this is F1 acted on by tau 1, and this part is F2 acted on by tau 2. And what we want this picture to be unambiguous. So what I would like to do is I would like to extract a single permutation. So maybe I'll put that in blue. And that single permutation is this right here. So here we've got the single permutation. What does it do? It sends 1 to 2 and 2 to 1, and then it sends 3, 4, 5. Okay, so this is a single permutation, and I can have it act on the operatic composition. And this is going to be my definition of an operation that we're going to later call beta. So beta for block sum of, in this case, like a tau 1 and a tau 2. Tau 1 was an element in the symmetric group on 2 elements, so it's in sigma 2. Tau 2 is in sigma 3. This thing is then in sigma 5. And so the axiom, and I'll just put it up here, is that this operatic multiplication has got to be equal to mu of G F1 through Fn. And now we just act by beta applied to tau 1 up to tau m. Okay. This is the first equivariance axiom. And the second one, as you probably can guess, is about acting on the first coordinate, the one before the semicolon, in the operatic multiplication. And this is going to define another function that we're going to call delta for duplication, because it's going to sort of take your permutation and duplicate inputs. Okay, so I'm not going to write down how this works as a formula, but I'm just going to draw you a picture. So let's say we once again have a G that's in P3. Here's a permutation. And now I'm going to take this G. So this is my G dot sigma. And I'm going to put in some more elements from my operad. So what if this is the picture I drew on my piece of paper, so I have to stick with it or I'll mess things up. Okay, so there's an F1 that at the top that has 2 inputs, an F2 in the middle that has a single input, and an F3 at the bottom that has 3 inputs. And what we do here is we sort of comb the permutation past the operatic multiplication. So I still have G, but when I do that, now the F1 that used to be at the top has to be at the bottom. The F2 that used to be in the middle, it now moves to the top, and the F3 that used to be at the bottom is now in the middle. But I still need to match up all of the inputs so that the inputs of my new thing are the same as the old ones. So that means I need a permutation here. So let's see, this one was in the middle. These two, oh, nope, that's not right. Let's try again. Okay, one is definitely in the middle. Oh yeah, it's because this is 2, and now this is 3. And so this permutation here, this is going to be my delta of the permutation that I had. So start with, I'll just write it as sigma, although in this case it's what 132. And you can see that this thing now is actually an element in the symmetric group on 6 elements. And I should note that there's not just a single delta. Delta depends, once again, like mu on some subscripts. In the case of mu, you can always recover all the n's and the ki's just by inspecting the elements that you're working on. But here we had to know both the degree of G and the degrees of each of the fi's in the order that they appear. So we know how many times to kind of duplicate each element, because you can see that the delta of sigma looks like sigma, just with the strands replaced with kind of multiples of themselves. Okay, so in order to have some good axioms here, we need these betas and deltas to satisfy some equations. The short version is that beta is a group homomorphism. Delta is not a group homomorphism, but it is kind of close once you keep track of all of the subscripts. And so that is what you get for an action operad. These determine the axioms for an action operad. So let me tell you what those are. An action operad has groups for each natural number. It has functions that look like operatic multiplication. It also has some underlying permutation functions, pi n, that goes from lambda of n to the nth symmetric group. And these need to simultaneously be group homomorphisms at each level and a map of operads from lambda to sigma. And then there's one final axiom that I've listed here at the bottom. This is essentially both of those. If you got the axioms for the betas and the delta right, kind of put those together, you get a thing that looks like this. I won't try to decode this for you now. Okay, so here's some examples. If you've got the identity functions on all the symmetric groups, then that makes the symmetric groups themselves an action operad in their terminal. If you take all of the trivial groups, then that'll be the initial action operad. If you take all of the braid groups and look at the underlying permutation of a braid, that's also an action operad. There are examples of this from homotopy theory that look at variants of the braid operad, like ribbon braid groups instead of braid groups. But anything that looks kind of like this, you can make into an action operad. And finally, if you take an operad in the category of groups using the Cartesian product, then you can give all those groups the zero map from G of n into sigma n. That will make G into an action operad. And in fact, the subcategory of action operads for which this underlying permutation map is the zero map, that is exactly the category of operads in the category of groups under the Cartesian product. Okay, so I mentioned at the beginning that this is like how you apply the adjective symmetric in front of the word operad, and every action operad lambda has a corresponding notion of a lambda operad, but we're not going to talk about this here because, like I said, I want to focus on presentations. So how do we get this? If we've got an action operad, I'm always going to write en for the identity element in degree n. And we can define these functions beta and delta using these identity elements. So beta of a string of f's is given by doing operatic multiplication, where G is now en, and then you just keep all the f's. And if you kind of swap where the identities are across the semicolon, you get delta. So delta of G, and remember, we have to have these subscripts or we won't know how much to duplicate. That's the operatic multiplication applied to G, where I've like fed in all of the identity elements at different degrees. Conversely, if you've got some groups and some underlying permutation maps that you think should constitute an action operad, then you can try to make the operatic multiplication by defining the operatic multiplication of G with a bunch of f's as the appropriate delta of G times beta of all of the f's. And the first theorem I want to tell you that Alex and I proved was that there's a bijection between action operad structures on lambda and these functions beta and delta, and then we have a list of 9 axioms that they have to satisfy. I wanted to point this out because the operad structure on the symmetric groups, if you go and you just try to write down a formula, you will write down this formula that defines mu in terms of beta and delta. So beta and delta are often much easier to get your hands on than trying to do the operatic multiplication all at once. Okay, so moving on to presentations. First, there's some kind of general theory of locally finitely presentable categories that'll tell you that you can make presentations for an action operad. So I'm going to write this like script S for the disjoint union of the underlying sets of all the symmetric groups. So I have all the permutations, but each permutation knows which group it comes from. So we proved, and this is a fairly straightforward kind of proof, that the category of action operads is a variety of S-sorted finitary algebras. So this just means that to give an action operad, I need to give you operations of arity, some permutation in some symmetric group. This means in particular that the category of action operads is locally finitely presentable, and there's a finitary adjunction between the slice category over this script S and action operads, with the left adjoint going from the slice to action operads. So how does this left adjoint work? If you've got the nth symmetric group sitting inside of S, then how do we like form the appropriate elements of the free action operad on what's called a collection? So our collection is a set over script S. We can look at the inverse image under this map F of the nth symmetric group, and we know those are elements sitting in degree n. So we start by forming the free group there. But an action operad needs operatic multiplication, so then we have to do that. We have to make sure that the multiplication in the group and the operatic multiplication satisfy the action operad axioms. And that's kind of step one. And then you just keep doing this back and forth. You like put some more group multiplications in, then you put some more operatic multiplications in, then you impose some axioms, and you continue going in a sort of standard inductive construction of the left adjoint. Okay, so a presentation for an action operad is then going to be two collections over S, two morphisms between the free action operad on R to the free action operad on G. So here G is going to be like our collection of generators. R will be our collection of relations. And then a final morphism of action operads from the free one on G to lambda, such that P is the co-equalizer of S and T in the category of action operads. This is exactly how you write down a presentation for a group. You take a free group with the generators, a free group with the relations, two morphisms between them, and then you have that your group co-equalizes those. Okay, as should be clear, this is like a fairly complicated presentation mechanism because you can start with a very small amount of data, and then you make free groups and then operatic composition, and then more groups, more operatic composition. So this gets quite large. But I want to talk about it from the perspective of clubs. So action operads are actually a sort of incarnation of a certain kind of club. And the point I want to make is that the presentation for the action operad just is a presentation for the club. I'm going to write P for the groupoid, that's the disjoint union over all the natural numbers of B sigma n. So this is, you know, a single object, and then a sigma n worth of automorphisms of that object. Okay, so a club over P is a category K and a functor little p from K to this P that sort of picks out the underlying permutation, and then it's got a multiplication from this thing that I will not explain, K circle K to K, and a unit functor 1 to K, satisfying the axioms for being a monoid in the category of P collection. So this circle is this kind of composition product. If you're familiar with the T operads of Leinster, then these are the T operads, where T is the free symmetric strict monoidal category monad. Okay, so how do we get between clubs and action operads? First, if you've got an action operad, then you can take the disjoint union of B and now lambda n, and that's a club. We've got this underlying permutation map from lambda n to sigma n. That's the lowercase p that we needed before, and the operatic multiplication just becomes the multiplication in the club. Furthermore, if you have a club such that the category K is a groupoid and P is bijective on objects, then that club is an action operad by the previous construction. Essentially, the automorphisms of the natural number n, that'll be your group lambda n, and then you just have to compare the operatic multiplication with the sort of club composition product. Okay, so now the main theorem I wanted to tell you about was this the fact that presentations for the club and presentations for the action operad are the same thing. So if I've got an action operad lambda and I've got a presentation for it, so it's got a collection of generators, that's bold g comma little g. It's got a collection of relations, bold r comma little r. It's got s and t that pick out the two things that get related, and it's got p that co-equalizes them. Then I can look at the club B lambda, and as a club, it is generated by, first of all, functors giving the unit object and the tensor product, and second of all, a bunch of natural transformations. And the natural transformations, you have one for every element of your set of generators. And if the underlying permutation, so that's this g of x, is some sigma sub x in the symmetric group on some number, then that gives a natural transformation, alpha sub x, from the tensor product of this, like, what I've written is kind of absolute value of x, the degree of x, the tensor product of the degree of x many elements, to the tensor product of the degree of x many elements, but now shuffled up by sigma. And the relations are the following. You've got the monoidal structure. That is a strict monoidal structure. The transformations alpha are all natural isomorphisms. This is not required in the definition of a club. And then for every element of the set of the collection of relations, we get that sign of the left side is equal to the right side. Okay, so here is the definition of a symmetric strict monoidal category or a permutative category to kind of show you how this theorem works in action. So one of these things has a category M. It's got a monoidal structure that I'm going to write as O plus with a unit object I'll write with 0, and a symmetry isomorphism beta that just swaps x plus y to y plus x. And it satisfies, these need to satisfy 3 axioms. Strict monoidal category, once again, if you do the symmetry twice, you get the identity. And then there's an axiom that tells you if you want to do the symmetry of a single object x with a sum of 2 objects y plus z, how do you express that in kind of elementary terms? Okay, if you want to express this using a club, you basically take this definition that you've gotten for symmetric strict monoidal categories, and you just directly translate it into the club language. So we've got binary and nullary operations to give us plus and 0. We've got a single natural isomorphism beta. Its underlying permutation is just the unique non-trivial transposition in sigma 2. And then we have axioms that correspond to the axioms in the definition. So there are the strict monoidal axioms, and then those 2 additional equations that I wrote down. So how does this work for the action operad? Well, the terminal action operad consisting of just the identity elements, that's a sub-operad of every action operad lambda, and the algebras over it are the strict monoidal categories. This means in our presentation, but we don't need to include anything about the strict monoidal structure. It all comes for free. That means our collection of generators just has a single element in it, and it's beta, and it lives in degree 2, and it maps to the transposition 1, 2 in sigma 2. And then the collection of relations has 2 elements. So you're supposed to think, when I write these down, that there's like an A1, that's the first equation, that's an element, and an A2, that's the second equation, it's the second element in R. A1 is in degree 2, and A2 is in degree 3, and then this part is what you get when you apply S to A1 or A2, and this part is what you get when you apply T to A1 or A2. And you can see that these use both the operatic multiplication and I've written dot for the multiplication in the group. And so here you can see that we've got things that look both like beta and delta from the beginning of the talk. So the corollary of this is that this presentation with a single element in degree 2 and two relations, one in degree 2, one in degree 3, that is a presentation for the symmetric groups as an action operad, not as a sequence of groups. I will point out that it's, depending on what your definition of fun is, a fun exercise to just start with this presentation of an action operad and the standard presentation of the symmetric groups using transpositions and show that this is in fact a presentation for sigma just directly. And that's where I want to stop. Thank you very much.
Thank you. And we have plenty of time for questions or comments. If people want to, they can unmute themselves and ask.
I don't know who was first.
Sorry?
I don't know who was first. We have two hands. Oh, no, they're clapping.
I think that's clapping. Yeah.
Oh, indeed.
I can start with one while the other think. Is there a notion of algebra for an action operads, and is it relevant for the stuff you're doing?
So you can certainly look at the algebras, but the kind of more useful thing is to take an action operad, form the lambda operads for it, and then look at algebras for the lambda operads. Now, the kind of theory I presented here is secretly doing that. So this, let me go back. So this, like, let me find my B lambda. Yeah. So this B lambda is actually obtained by taking your action operad lambda, and then that's an operad in the category of sets. You can apply the indiscrete category functor to that, and you'll get an operad in cat now. That is an operad, and it is a lambda operad. It kind of still looks a bit like lambda, but now sort of made indiscrete as a category. And then this category B lambda is what you get when you apply that lambda operad to the terminal category. So really, the more useful thing usually is to look at the lambda operads and their algebras rather than the algebras for lambda itself.
Okay, thank you. Anyone else? If not, then let's thank Nick.